Honors Chemistry, and welcome to the last section covering the last two sections of Chapter 12, Intermolecular Forces. So we have referred to these all year, right? We've talked about how one molecule stays next to another molecule as a solid or liquid because there's an attractive force. We've talked about why boiling requires the input of energy because we have to break said attractive force. Now we put some formal labels on those attractive forces, rate them by strength, and you, courtesy of your Lewis structure drawing skills, right, and Vesper knowledge, can go ahead and decide which IMF belongs to which molecules. So first of all, we have LDFs, which is pretty much an attractive force between anything with electrons. And the strength of an LDF is based on the total number of electrons, right? And this is an instantaneous dipole, right? Where we talked previously in the last chapter about a dipole is a molecule that's polar, okay? Turns out that there are a lot of non-polar molecules and just atoms that experience attractive forces because at any given point in time, since electrons are constantly moving, they can be unevenly distributed. And if they are unevenly distributed at one instant, then for that instant, that atom or molecule is polar, right? Which then it can induce that same polarity in its neighbor, which can then induce it in its neighbor, and we get this network of instantaneous induced dipoles, okay? And that's what an LDF is. So if we're going to rate the LDF of one thing relative to another thing, it's simply based on the total number of electrons. So if I asked you to compare the LDF between Cl2 versus I2, right, first you would need to decide, well, are LDFs the only IMF? And the answer would be yes, because these are nonpolar molecules, right? So that would be step one. Step number two, which has the greater total number of electrons? Therefore, that one has a stronger London dispersion force, or a stronger force of attraction between molecules, which means we can draw conclusions like this one probably has a higher melting point and boiling point, yes? And a higher viscosity, if that's what we wanted to talk about, if they were both liquids, right? And other properties like that. Yes? Makes sense? All right, let's go ahead and add on some other types. And so that applies to everything with electrons. Next up, we have dipole-dipole, right? So this is a force of attraction for polar molecules, which means that in order to figure out if something is polar, first we would need a Lewis structure. We would use Vesper to then come up with its three-dimensional electronic and molecular geometry, and then we would know if it's polar or not, and if dipole-dipole is also an attractive force between molecules of said thing, right? So these are molecules that have a permanent polarity to them, right, as opposed to that instantaneous sense of polarity for LDFs, right? How polar a molecule is also depends on its shape, though we're not going to get much into that. So then something that has dipole-dipole forces is probably going to have stronger forces of attraction than something with just LDFs if they are comparable in size, okay? Which then brings us to this example from your guys' book, right? So they give you the molar masses, so that way it shows you that, oh yes, these are comparable in size, but we see that the boiling point of this molecule is much higher, right? The boiling point of formaldehyde is much higher than ethane, which then, even without their structures or their formulas, would lead you to conclude, right, the attractive forces of formaldehyde are greater, yes? The fact that it has a higher boiling point, if you knew nothing else, tells you that the attractive forces are greater. Then if we look at the formula and the structure, we can see, oh yeah, I can see that. See, we have an oxygen molecule here, right? Here, everything is evenly distributed. And again, we'll look at how to gauge that a little bit better in class. But this carbon only has three things, right? So it's trigonoplanar, one of which is different, which means it's polar, right? That goes back to whether all the groups are the same or not, right? Here, this is tetrahedral, and they're all the same, so nonpolar. Then that brings us also to hydrogen bonding, which is very specific, right? We have to have a hydrogen bonded to an FO or N, okay? Must meet that criteria. And then it is attracted to lone pairs on neighboring, on neighboring FO or Ns, right? So it must meet that whole definition to qualify for hydrogen bonding, okay? H bonded to FO or N and attracted to lone pairs on neighboring FO or Ns, okay? Now, that brings us to these examples here, right? Methanol and ethane, where again, similar in size, but we see that the boiling point of this molecule is much, much higher, So it tells you that whatever is happening there, right, it's got much, much stronger attractive forces. So when we look at our molecules side by side, right, when we look at their structures, not only does this have LDF and dipole-dipole, it also has hydrogen bonding, right? And intermolecular forces add together, right? So if something has all three of these, odds are it's going to have a higher boiling point than anything that has only one or two, okay? Which also leads to a lot of water's unique properties because it is also LDF, dipole-dipole, and hydrogen bonding. And then we get ion-dipole, which is only ever something to consider when we have ions in the presence of dipoles. So pretty much this is anytime we have salt in water, and this would be the resulting force of attraction, okay? All right. Then that brings us to our crystalline solids, right, where we can have a molecular solid, which means it's made up of molecules or molecular compounds, right? And molecules would be the word that describes the particles, and they have relatively low boiling points because they're held together by, right, intermolecular forces, which are weaker than actual ionic bonds, right, or covalent bonds for that matter, okay? IMFs would be weaker than all of those in general, though there are always exceptions, right? Then we have our ionic solids, which have very high melting points because we have actual positive and negative charges, right? When we talk about IMFs, we're talking about partially positive and partially negatives. Ionic compounds have full positive and full negative charges and whole networks of these, which leads to a really strong force of attraction. Then we have our atomic solids, which are made up of atoms, clearly, right? And their melting points vary a lot, which means that the force of attraction between atoms varies a lot depending on its properties, which then brings us to here, where we can have our metallic solids, which are held together by metallic bonds, which our book sort of talks about being a sea of electrons, where our electrons are delocalized. What does that mean? Right, they are not stuck to just one atom. They are spread throughout the metal, right? Because we talk about metals have a tendency to lose electrons. So what that means is all the atoms stuck together, a lot of them, their valence electrons are not tightly held, so they can sort of spread throughout the entire sample of a metal, which is why they conduct electricity well, right? Because there can be a flow of electrons through it, okay? Then we have our non-bonding ones, right? So these are ones that are, this is pretty much everything else. So if it's not a metal, it's most likely a non-bonding one held together by LDFs with relatively low melting points, okay? Then we have a rare few that have covalent bonds that hold them together, right? Silicon is one example. Carbon, two forms being, right, graphite and diamond, right, are also some exceptions in that those are covalently bound. Okay, which lead to their unique properties, by the way, right? Like diamond has some unique properties, graphite has some unique properties, which you should be able to tell me about next class period, yes? Fantastic. All right, thanks for listening, be good, and I will see you soon. Bye.